Perfect. Welcome everyone and good afternoon. I'm Jen Roberts from the University of Strathclyde up in Glasgow and also a member of the UKCCSRC Directorate. I just wanted to point out for those that are feeling a bit chilly towards the front of the room that it's actually a lot warmer at the back of the room, and those who are sweltering at the back of the room, it's cooler at the front. So if you're feeling like body temperature issues, then just by all means just move around the room. I also really want to make sure that we keep to time. We're already 5 minutes late. And I want to make sure that we finish on time. So I'm going to try and keep things quite crisp and clipped and time-wise. So today we've got 4 speakers. We've got Clare Bond, Vahid Niasar. I'm not quite sure how to pronounce Vahid's name, so hopefully he can keep me right. Chris Holdsworth and Wang. That's the order we're going to take them in. And what we're going to do is we're going to have each speaker, and then we'll have a short amount of time for Q&A. If I can, I'll then move things forwards to allow for a little bit more time at the end. But ultimately, we're just going to be capturing any further questions outside of that time will just be the questions you ask each other when we go to the posters and the networking dinner. So without further ado, I'm going to hand over to Clare for the first presentation. Thank you very much, Clare. I'll let you introduce yourself as well.
Go. So my name's Clare Bond. I'm a professor at the University of Aberdeen, but I'm really here in my capacity as a very chief scientist. It makes it sound more exciting maybe than it is, for the CO2 storage research facility. And so I'm come here today both to tell you a little bit about where we are with the project, but also to really get your ideas and thoughts about what a CO2 storage research facility might mean for you, and to get ideas. And I'm going to put an email up at the end that you can email if you want to be on future mailing lists. And I'm also going to put up the Science Advisory Group members. So I chair something called the Science Advisory Group, and they are really there to represent the community. And I've kind of given them specialities in that list, but hopefully you'll identify with somebody on that list, and they're your kind of go-to person for input into the project at this stage. So our mission is to deliver a novel, world-leading geological CO2 storage facility for fundamental and applied research and innovative technology development informed by community needs. And you are part of that community. So yes, that's why I'm here. And it won't surprise you really, I suppose, that we're, it's all about the kind of the current political agenda in many ways, both nationally and internationally, in terms of supporting the UK's drive towards net zero and CO2 reduction, enhancing the UK's reputation as a science superpower, and thinking about improved regulation and informing public dialogue around carbon capture and storage. So the idea is that there is kind of broader benefits for the UK of having its own CO2 storage research facility. So I've got a little history up here. I'm just going to talk you through this just so you kind of know where we are now and where we're going. So pre my time in kind of 2018, 2019, there was the start of an initial idea for a UK carbon capture and storage research facility, I guess backed by the European Green Deal and other kind of policy actions at that time. But at the start of 2020, UKRI got some infrastructure funding, so £500,000 to do that. To do a scoping for what was at that stage called COSLab, or CO2 Storage Laboratory. And this was all led by NERC, and I'll come on to that in a minute. At the same time, UKRI had a kind of looked at its strategic and policy documents, and CO2 storage and the potential for some infrastructure kind of sat within two of those strategic documents. A science steering committee was established, and I started to get involved then. So I started to chair that science steering committee. So then we started this phase 1 scoping study that was led by the British Geological Survey. And there was engagement both with research and the industrial community and some regulators and stakeholders. And there was a series of workshops that some of you may have attended on social science, site characterization, monitoring on conformance and well integrity, I guess is how I describe it. And that ran until the end of 2021, start of 2022. And there is a report that's come out of that, which I'll highlight in a minute. Then in 2022, there was funding for a second stage of scoping. So this is now £2 million of scoping. This is really for the British Geological Survey to look in greater detail at potential areas where we might host such a storage research facility, to do further engagement and to really take that scoping forward to applying for infrastructure funding. So it's had a few names. It was also known, if you ever hear a CO2 testbed as well, it's also been known as the CO2 testbed, but it's currently called the CO2 Storage Research Facility, or occasionally the Carbon Storage Research Facility. And at that point, we had a kind of a more formal science advisory group. And we're at the stage now where we're looking to put in an infrastructure fund bid in July. So the idea is it'll go to the NERC board in June and go for full infrastructure funding in the summer. So I said UKRI, kind of the body that's hosting this, are leading on this, and within that it's NERC that are taking the lead. So for those of you who are maybe more EPSRC focused, NERC is effectively focused on environmental science and putting environmental science at the heart of responsible management of our planet. So NERC at the lead, but obviously you hopefully can see synergies to Innovate UK, EPSRC, ESRC, AHRC. So it's kind of cross council, I guess, in that framing, but NERC at the lead. So, and these are the two strategic documents just from 2020. So one is about landscape and thinking about environmental capabilities from micrometers to kilometers and minutes to millennia. So it fits in with that as a kind of framing. And then particularly for infrastructure, CCUS was identified as a priority theme for infrastructure. So it's kind of was written in 2022 into the UKRI kind of strategic documents. So phase one scoping, there is more, yeah. There's this PDF you can download from this link. All these slides and this presentation is going to be available. So you can download this report, which was the culmination of the phase one scoping. And it summarizes the community engagement that took place through the phase one scoping. Oh, sorry, just go back. So at that point, the BGS engaged with 56 individuals representing 24 stakeholder organisations, and it also asked for some written submissions. So you may have also submitted a written submission, but that was the breakdown of the types of organisations and individuals that were represented in that engagement. They also, the British Geological Survey also at that time looked at international facilities and other pilot and demonstration projects. And I've just split them up here. There's kind of 16 key ones, and you can see the different focuses. And as part of that kind of scoping and looking at those international research facilities, I guess it was really clear that they were mainly all designed to answer very specific research questions that had quite a national focus. And a lot of them had very set research plans, so some of them have actually finished. But as a consequence, that there was this thought that we needed something for the UK to answer specific UK questions. So as part of the scoping, there were some kind of key science objectives and research objectives that were identified, and I've summarised them here. So they're predicting, verifying and optimising trapping efficiencies, demonstrating permanent containment, advancing in situ monitoring, developing storage failure scenarios, and public engagement came out as the key kind of research objectives or challenges, depending on how you want to describe them. And in that scoping report, there was also the start to look at infrastructure options. Everything from kind of business as usual and linking to the track 1 and 2 clusters, which are 1 and 2 here, through to different kind of bespoke setups for a research facility. And the preferred infrastructure options, so a couple of infrastructure options have been kind of taken forward in the planning, but the preferred infrastructure option is for an on to offshore facility. So going out about 2 to 3 kilometres from, so being in the near shore, but at a depth, so about a kilometre depth, so a depth where we can inject dense phase CO2, and then potentially to have some onshore facilities where we test things like well integrity and other issues. So it's quite a big project, and the idea is also that there's a big digital infrastructure part of it as well. So where are we now? We are in this phase 2 scoping, and again, this work is being led by the British Geological Survey. So Jonathan Pearce is the kind of chief technical officer person. I don't know how quite he changes this title, but he sits on the executive with myself and Simon Durbin at NERC, who's a project manager. So we sit on an executive team. And then we've got Maxine Atpearce, Jim White, Kerry Vincent and Hazel Napier, all within the BGS, who are leading different work packages. So I said I'd put up the Science Advisory Group members. I'll leave this up for a minute. So this is the current Science Advisory Group. And you can see, hopefully, I've given them like titles like geochemistry, geophysics, but it gives you a bit of an idea as to kind of the specialities of the people involved in the Science Advisory Group. I'm not going to read out all of their names, but these are the current people that are involved in helping to kind of shape and form the science questions that will be addressed. So yeah, we can see we've got quite a range in there, which is great, from industry representatives, well engineers, arts and humanities and social science. So this kind of breadth within the Science Advisory Group. And then, yeah, this is just the email to leave you with. So if you're interested in kind of being involved in the future, if you want to input any thoughts and ideas, be on future mailing lists, this is the email that you should email. So I'm here for the next day, I guess, today and tomorrow. Please do come and chat to me. We're really in the stage where we're doing costings and talking to regulators and defining what science questions we can address with the infrastructure. So just please come and have a chat, come and talk to me about the project and your interests. I'm sure there's a zillion and one questions. Thank you, Claire. I think,
yeah, we're great timing wise, so thank you. We're 30 seconds under. So do you have any questions from the floor? We've got 3 very helpful helpers ready on hand with microphones. Any questions? Yeah, one in the middle. And then we'll take Stuart after that. And then
Hazel. How's that? Right, Stuart Hazeldine from Edinburgh. I'm just wondering how then, obviously you can make a choice about a site, but does that really address the sort of 6 or 9 objectives which you'd put in 2 or 3 slides beforehand?
yeah, so BGS have looked at several sites in terms of kind of where we could actually do this practically. And that search has narrowed kind of considerably to a preferred site. You cannot obviously address everything. So there are questions, say, around depleted reservoirs, for example. And so we have had chats with, so we have a task and finish group around kind of flow assurance, and we have had chats around whether we could kind of recreate scenarios that would allow us to test some of the questions around depleted reservoirs and injection and depressurization. So there are leaky borehole.
Yeah, leaky boreholes.
Yeah, so we have had some chat around, say, if we have an injection well and then we had a monitoring well, like could we use that as a proxy for a leaky borehole, for example, or for the onshore, whether we could drill something nearby and look at that connectivity and pretend it's a 1950s well with not so great cement. So some of these scenarios are kind of being discussed at the moment. We're not going to have everything this. You never can. The list is massive, but yeah, there's a lot of discussion around what we hope we can address.
What we prioritize. Can we? So the first question was, yeah, this gentleman here.
Hi, thanks, Claire. I'm David. I'm a net zero PhD student at Keele, and I'm also a reservoir geologist at Merlin Energy. I have actually read that BGS publication. It's quite helpful for my research. And looking at that list of Science Advisory Board members is quite sort of academic heavy. I was wondering, you know, the outputs from this project, are they being taken on board by the OGA, NSTA, whatever they call themselves these days?
Yeah.
Are these things being taken on board by them and sort of informing, you know, the site selection process and the kind of screening that they do in-house?
Yeah, so we've got just ongoing discussions with NSTA. NSTA were involved in the well flow assurance workshop with exactly those questions about leaky boreholes. We have Matt Taylor from Department of Energy Security and Net Zero. I did it. Who actually sits on a project board as well. So the Science Advisory Group, there's somebody from Department of Energy Security and Net Zero who comes to our Science Advisory Group meetings as an observer. So there are other people that come to the Science Advisory Group as observers. And then we have somebody from DESNZ who sits on our project board. So yeah, so there's a good link into government through there. And effectively, it'll either be DSIT or DESNZ who will eventually fund it. So that, yeah, there's quite a strong link into industry. And we have, yeah, separate chats with HyNet and Northern Endurance Partnership. And we're also really interested in the licensing round announcements, which are due maybe at the end of the month, who knows?
Much was promised for the end of the month. Okay, fantastic. There were a couple of other questions as well, but we've run out of time. So we're going to, sorry, it's 3 minutes for the questions. So quick questions and quick discussion. Moving on, we've got our remote presenter joining us now. Hello.
Hello, can you hear me?
Yes, fantastic. Hello, lovely to meet you. I haven't met you before.
Yeah, indeed. It's unfortunate that I could not join in person. It is probably one of the features online because just literally 10 minutes ago I was presenting in a conference in Manchester. So, so two presentations in one day.
Yeah, well, it's only been knackered tonight. I haven't been doing any formal introductions at all. So are you okay if I hand over to you? You've got 12 minutes and are you happy to introduce yourself as well?
Absolutely. Thank you very much. So I go quick. Hello, my name is Vahid Niasar. I'm a professor of subsurface engineering for media physics at the Department of the Chemical Engineering, University of Manchester. I joined Manchester in 2014. Before that, I was working for Shell. So today I'm going to talk about the physical chemical aspects of the basically CO2 storage in saline aquifers. It is a PhD work that my former PhD student Hamid Reza Irfani and Sen Yuan, they did, and thanks to my colleague Masoud Babai. So talking briefly about my team, I started in 2014. As you can see, basically, I have worked mostly on porous media physics and with the application of subsurface. We do two types of the research, I would say, that they're hand in hand. One is experimental work from the porous scale to core scales. For example, what you see here is the porous scale experiment of solid transport in kind of synthetic porous materials, 2D systems that are made of the PDMS or glass, and we based on the open microscope that we designed it ourselves. And also we do porous scale modeling and continuous scale modeling. That in the examples we show here, it's one of them is the classical advection dispersion on the right side, and on the left side you can see the non-Newtonian fluid flow and transport in porous media using different porous scale models that we have developed in our team. And with these technologies, experimental or computational, we're going to address different applications: CO2 storage, recently hydrogen storage, a bit of geothermal, and also in other applications like fuel cells, redox flow batteries, soil and environment. So going back to this discussion of the CO2 storage, I can skip this one. You know that CO2 storage is one of the basically a part of the solution to reduce the carbon emission to the atmosphere. And we know that when you inject the CO2 under supercritical conditions, initially it is two-phase flow near the well, but because of the gravity segregation, so the CO2 overrides the brine system if it injects into the saline aquifers. And over the time, the CO2 starts to dissolve into the brine. So this presentation is not about the two-phase part. I mean, a part of it will be about two-phase, but majority is about when the CO2 has dissolved. So basically looking at the top side, and we look at the natural convection due to the CO2 dissolution into the brine. So these are the equations that we have solved at the continuum scale. So we have Darcy's law, we have solid transport with the dispersion term that it is flow rate related. So it is not only purely diffusion. And then we have the density effect that depending on the concentration dissolved in the brine, the density will change. So as soon as the density is changing, you start to penetrate the heavy fluid inside the light fluid, and there is no capillarity between them, just keep in mind. And then we have some dimensionless numbers. The most dimensionless number is the Rayleigh number, that it is the density difference times the gravity times the permeability of the field, depth of the reservoir, porosity, diffusion or dispersion coefficient, and viscosity of the fluid. This is the numerical domain that we have had. So closed boundaries, and at the same time at the top, there is a CO2 gas that it is dissolved in the system. So we don't look at the capillary force at the top. We just look at after dissolution, what happens. To make it more complex, we also couple the in-house developed continuous scale model with the geochemical reactions. We look at the sandstone carbonates. In this case, we show because the carbonate reaction is more enhanced compared to sandstone, we look at the typical reactions. I'm not a geochemist, so I don't have any claim. We just simply follow the literature based on the geochemical, and then we use the pre-QCRM for coupling with the flow simulator. Then another thing that we look at it is the flux, that is the flux of the dissolution, so or dissolution rate. So defined by F here, that it is the mass of that it is dissolved by time over the area, that it is in contact. And if you look at the literature, you always get these onset, basically this type of the graphs that they show the flux versus in the logarithmic scale versus the time that is logarithmic scale. So if you look at the long term of the CO2 storage in the subsurface, then we can see how does this dissolution takes place. So we have different, depending on the reservoir, because now based on the Rayleigh number that I introduced initially, that's a key parameter here, depending on the permeability, depth of the reservoir, and so on, the height of the reservoir and density different and so on. So you can define different Rayleigh numbers, and you can run simulators for each of them separately. And you see that this convection flux, how does it take place over the time? As you can see, in the low Rayleigh number in 1500, the fingering is very, very small. But when you increase the Rayleigh number, the fingering is enhanced. And this has the key message that, okay, we enhance the fingering, the solution gets higher, and then the flux of the transport from the basically dissolving of the CO2 into the brine, that which is a good thing that we want in the saline aquifer, enhances. Now, the question is that a scientific question basically is whether it is important to include dispersion. For those who are not familiar with the concept of the dispersion, we have two terms in transport usually. So one is the diffusion. That means there's just simply by molecular diffusion or gradient of the concentration from high concentration to the low concentration. Or the second one is that, no, you have a flux and the velocity component, and that leads to the dispersion. In porous media, dispersion is classically in hydrogeology, it's very important because the solid transport, contaminant transport has been important. So the question was that in more simulators, when we do not include dispersion versus the case of the inclusion, what would be the change of the behavior of these flux, dissolution flux versus the time? As you can see here in these graphs, again, the same class of the Rayleigh number that I discussed, I showed the videos, 1500, 6000, and 100, and 12,000. As you can see, the red guys, they show the alpha L over H means dispersivity. So with increasing the dispersivity, the flux of the dissolution gets enhanced or gets bigger. So that means the hydrodynamic dispersion instead of the only diffusion results in earlier onset time and higher flux. And at the early time or at the very diffusion control system, these differences of the hydrogen, of course, so the difference between the hydrodynamic dispersion without and with is not that significant. And also the dispersion will lead to the thicker fingers or basically with fewer plumes to be generated in your system. Then we go to the concept of the geochemistry. So now the first case was the benchmark case, basically diffusion. Then we added more complexity, included dispersion. And now we add another complexity is that if you add geochemistry into the model, what would happen to these dissolution fluxes? Clearly here we look at the carbonates as we have written the text. So the geochemistry included for carbonates. So, and then again, we did the simulation based on this natural convection. And as you can see, with including of the geochemistry for the carbonates, you can see that the pH decreases in the swept area, as you can see in this figure on the right top. And then we can look at the concentration of the different species, for example, calcium. And we see that the acidic water will dissolve the calcite and dolomite from the aquifer and will increase the concentration of calcium and carbon in the swept area. And overall, we can conclude based on the graphs that you can see, the reactive versus the non-reactive. So the reactive ones are the continuous lines and the non-reactive are the dashed lines. As you can see, the geochemistry will promote the enhanced convective mixing and result in early onset and higher flux in the convection-dominated regime. So this is the third learning points. And also you can look at where the precipitation or dissolution happened. As you can see here, we can see that, for example, we have the gypsum precipitation shown here in which areas, and then we have dolomite and we have calcite. So it's a kind of output from the model if somebody is interested in the geochemistry, that how these models can help, that geochemistry and flow, they can be coupled together to get a better understanding of the dissolution precipitation during the CO2 injection. Now, another question is that another finding from the paper is that from this research is that we found that the porosity change is almost negligible in our simulations. So we did not see at least a major change in the porosity. And if it is not a major change, so that means the permeability field and flow field would not change dramatically as a result of the geochemistry. So it has more effect on the dissolution flux rather than the geochemistry. Now we go one step, actually not one step, one scale lower. So from the continuum scale, this is another showcase, is that we tried as well to see if we go to the pore scale, how we can understand the geochemistry, and how the key question is the upscaling of the dissolution rate. What we did in this work is that we developed the pore scale model, the same story. We have the carbonated system, carbonated brine, we injected to the rock, and then we look at we couple with the geochemistry model, and we look at the dissolution, and we try to understand at the pore scale, what is the dissolution rate that you can see here on the y-axis here versus the injected pore volume. As you can see, at early time, the dissolution rate that it is defined over the whole sample that you can see here, the dissolution rate starts to increasing, and after in the basically later time, it stabilizes that dissolution. And also with increasing of the flow rate, as you can see in this graph, with the higher pore volume injection, the permeability change, basically that it has been shown that how does it change as injection if you increase the injection rate. So this pore scale model, the key part, the message, the key outcome is that using the ProScale models, we can possibly better upscale the reaction rates. We did an ongoing project on the X-ray imaging of the same story. So what we did, two samples, as you can see, sample A, sample B, with major minerals that we found there. And we drilled a hole around 250 micron inside that. And then, and then after that, after that, we look at the dissolution rate, dissolution inside those rock samples. As you can see, depending on the geochemistry, some of them, they dissolve with time homogeneously. So the red part is evolved in the whole width, it is increasing. But for the second one, that it has anchorite in their composition, as you can see, as a result of this dissolution, the secondary mineralogy stays in place, and you have the secondary porous media resulted from that dissolution. So giving that, I don't know how much time is left, probably I'm over time. So what you can see that, okay, we have shown the ProScale models, continuous scale models, that we look at the dissolution of the CO2 in brine. And also we have looked at the upscaling of the reaction rates, because we believe that is the key to understand better the long-term behavior of the CO2 injection into the aquifers. So these are the follow-up papers, if you are, and basically the papers that you can see that, okay, this presentation is based on. And I think I can stop here because of the time, because these are the beyond there. So ready for any question or criticism.
Perfect. Thank you very much. Round of applause. We have only about 30 seconds for questions, so I'm just going to ask Vahid, do you have anyone from your team here at the conference today?
No, unfortunately, because as I said, at the same time, Manchester has this 2-day conference. Unfortunately, the team is in this conference in Manchester. They couldn't join.
That's no problem. I just thought if you did, then we'd basically be able to direct any questions to them. I was particularly interested to hear about your reflections on, or your findings on how your modelling changed, whether or not you were introducing any vertical permeability barriers, but it sounds like you weren't. But anyway, I think in the interest of time, we're going to have to just close you off there. I'm sorry. Thank you for joining us, and I'm grateful you were able to join.
Thank you.
Yeah, thank you very much. We'll now hand over to
okay. That looks good. Okay, so yes, I'm Chris. I am a PhD student at the University of Edinburgh. I'm not going to talk to you about my PhD today. I'm going to talk to you about Carbfix. So Carbfix are the industrial sponsor partner on my project, and they are a CO2 mineral storage company. So I'm going to speak a bit about CO2 mineralization, the journey that Carbfix have been on. And in light of our conference theme about geographically dispersed industries, I'm going to talk about Carbfix's flagship project. So that's called the Coda Terminal. And this is the world's first onshore CO2 mineral storage terminal that's being built in Iceland. So I'll come to that. But first of all, just in case anybody isn't familiar, I'm going to say a little bit about mineralization to start with. So Carbfix is all about this white stuff, this mineral here, which is calcium carbonate, or calcite as we know it. And what Carbfix do is they take CO2 from a variety of sources, dissolve it in water, and then inject it into some lovely rocks like this, like the grey rock here. So that's basalt core. It then reacts with the rock, and what they found is they can very quickly convert that aqueous CO2 into mineralized CO2. So that's a bit different from kind of the traditional geological CO2 storage that most of us are used to. So we're used to something in clastic rocks, something like this schematic here. And the key difference really with what Carbfix do is, so here we're using physical trapping mechanisms to securely store our CO2. So we're either using some sort of structural or stratigraphic mechanism, like an impermeable cap rock, and we're also making use of the pore space in our usually sandstones or other sedimentary rocks to physically store our CO2. What Carbfix are doing is they're chemically trapping the CO2, and we heard a bit about that in the previous talk, particularly solubility trapping. So that's what Carbfix do is pre-injection. They dissolve the CO2 in water. That creates a dense gas-charged fluid that when it's injected into our basalts, it's denser than the fluids around it. So you create a solubility trap, you kill the buoyancy of the CO2. And then because you've injected what is essentially an acid into the basalts that starts to react with the rock and pull out the calcium, magnesium, and iron that we need to form our carbonate minerals. So we end up with a mineral trap on the end there. So the kind of rough ingredient sheet that we have is we have some ultramafic or mafic rock here with our calcium, magnesium, and our iron in. We have our water dissolved CO2, and we rapidly form our minerals. So you end up with some sort of schematic scenario that looks something like this, where these are the two scenarios we have at Carbfix, where the CO2 is either dissolved down hole in the injection well, or actually on the surface here on the right. So that's how it works in practice. In terms of the journey that Carbfix have gone on to put that, to deliver that, and where they're headed, Carbfix began as an idea back in the late 2000s. So it was formed as a partnership between some Icelandic companies, the geothermal power company out there, and some academic institutions as well. And the first technological field test of this technology was back in 2012. So there was around 250 tons of CO2 was injected into the basalts near Iceland's largest geothermal power plant, Heriot-Watt. So it's about half an hour outside of Reykjavik. So that was the first field test, and the key kind of findings from that project, and I guess almost lift off for Carbfix as an idea and a CCS option, came from these graphs. So for any of the chemists in the room, what this is showing is that essentially, so you've got time on your x-axis passing, and Carbfix's verification is based on geochemistry. So using fluid traces, combination of reactive traces like radiocarbon and dissolved carbon, and pitching them alongside unreactive traces in the water. So what they found was, if you were to inject your CO2 and nothing would happen, and you'd recover everything as you injected it, you'd get the black dots up here. So on our x-axis, we've got time. On our y-axis, we've got our radiocarbon and our dissolved inorganic carbon. So if nothing happens, you should get these black dots. But what they actually found was you had these empty squares along the bottom. And essentially what's happened there is all of that carbon has been locked up into the minerals. So they found ultimately that over 95% of that, only a few hundred tons, but of the CO2 that they put in, was mineralized within 2 years. And obviously the almost 100% is a key number, but also the time frame is really key, because ultimately the conventional wisdom for CO2, the different trapping mechanisms, was that basically as you go from the physical trapping mechanisms up here to the chemical trapping mechanisms, you may be getting more immobile in terms of your storage, but it takes longer to get to that. In nature, that's generally what happens. To form minerals usually takes a long time. What Carbfix found in their scenario, when you dissolve the CO2 in water, is you can do that much quicker. So you can do it within months and years, which is obviously useful for why we're all here in terms of climate change mitigation. So that was kind of liftoff. Then for Carbfix came okay, let's roll this out to an industrial scale. So this inventively is called the Carbfix 2 project. It's a point source emission from Heriot-Watt geothermal power plant. It captures 12,000 tons of CO2 a year. It's then dissolved in water on the surface and re-injected into the geothermal reservoir that's come from via this injection well. It flows through, those fluids flow through the geothermal reservoir, so we can monitor what happens to that CO2 and also hydrogen sulfide that's co-injected in the water, so we can verify what's happening. And the latest data that has come out of Carbfix 2 that suggests over 60% of this injected CO2, so around 7,000 tons per annum, is mineralizing within 4 months of injection. So again, it's always crucial. Obviously, we want to focus on how much is mineralizing, but also the time scale that's happening is really important for what we're doing. So that's the industrial demonstration that's ongoing. It's been going now for almost 10 years. After, and in terms of the full kind of value chain, what Carbfix have found, now this is a very specific example for the geothermal sector, but what they found, their whole cost for capture, the majority of the cost comes from the capture technology. But in terms of the whole capture, transport, injection, and the monitoring, they're getting around $25 per ton of CO2 at this particular project. So that's the point source emission. Then Carbfix moved into the DAC space, the direct air capture space, and partnered up with Swiss company Climeworks. So this picture here is the world's first direct air capture with integrated storage project called Project Orca out in Iceland. It uses Climeworks' capture technology in these units here to capture 4,000 tons per annum of atmospheric CO2. that CO2 is paid for by carbon credits that are sold by Climeworks, and so the injection site is just about a kilometre away, again right next to the power plant, just outside Reykjavik. And one of the key outputs from this project so far for Carbfix is this publicly available document here, which is their methodology. It's essentially the scientific and the legal basis for how they verify their storage and the credits that are sold. And these types of documents are going to become so important in terms of giving legitimacy to these projects and showing that they're not just greenwashing. So that's the DAC space. There's plenty more going on in terms of that. But for the rest of my time, I want to talk to you about Project Coda, because Coda is ultimately designed as a CO2 receiving facility for industry sectors, whoever it may be, that have CO2, but they can't dispose of it on site because they don't have storage or for whatever the reason. So as I said, it's the world's first onshore mineral storage hub for CO2. It received just over 110 million euros from the Innovation Fund last summer. And it's located just between, so we're in Southwest Iceland, the international airport Keflavik is here, Reykjavik's here. It's just off the main highway that connects the two, so just down here in Stromsvik. So it takes you, so this is the main highway here, you're going out towards the airport in this direction and Reykjavik's behind us. It's making use of the existing aluminium smelter that's there, run by Rio Tinto. So it has very good electricity, renewable grids connection, has a port facility, and most importantly, has a big whopping lava field that obviously is crucial for our mineralization. So that's where Coda is. In terms of the idea, as I've said, generally it's going to offer low cost, secure mineral storage for all of Europe. So wherever the source of CO2 may be, whether it's from DAC, whether it's from industry, the idea will be it'll be shipped to Iceland. There will be up to 6 ships operating by CO2 shipping company Dan Unity, and they will ship to Iceland and exactly the same process, water dissolution, reaction with the rocks to mineralize and securely store the CO2. In terms of the costs associated with that, Carbfix, so these are the numbers that went into the European Commission for the Innovation Fund. Carbfix don't deal with the capture side of things, but in terms of the transport, at the moment, the transport fee is between 24 to 34 euros per tonne. There's a premium on top of that for green fuel, and that's obviously important for accreditation, because if you're not using green fuels, that's going to count against your carbon sums at the end. And there's also a storage gate fee of $13 per tonne at the end there. So that's the costs. And then finally, what I want to do is just walk you through the kind of scale up plans where Coda is heading and what the future looks like for Coda. So as I said, they got the money last year from the EU. The first well was drilled, appraisal well was drilled at the end of last year. The target is for this year, pilot injections of CO2 to begin. They are going to be happening alongside a lot of other R&D projects for Carbfix. So 2 that I want to mention, one's called Nespresso. So that's building on capture technology from a point source emission, kind of like the Carbfix 2 project I spoke about. And that's a modularized technology that will be ideally exported and tried in other locations. The other one that's really important is Project Seastone. So up to now, Carbfix have always used water that's associated with the geothermal or essentially fresh water. One of the big R&D questions for Carbfix is, can you use seawater in all of this? Because that will export the technology and open up a whole range of other places that you could potentially do this if freshwater stress is a problem, which it is in many parts of the world. So they're 2 big R&D projects. We've got pilot injections of CO2 beginning this year. The aim then is to get, by the end of 2026, be injecting 500,000 tonnes of CO2 per annum. Then beyond that, getting up to 1 million tonne, up to full-scale operations towards the end of the 2020s, before Coda gets towards its operating capacity, which is 3 million tonnes per annum by the early 2030s. And ultimately, the aim beyond that, there will be lots of learnings and challenges within that, is to then take that the hub idea and replicate it elsewhere. So elsewhere in Iceland and elsewhere in the world, because ultimately one of the reasons that mineralization has been looked at is because of this map. Ultimately, there are a lot of volcanic rocks in the world, and it gives us another tool in our storage arsenal to tackle this massive problem that we all face. So that's the ultimate challenge. And it's important to remember there are big basalts, both deposits offshore, but also in big areas that might not have clastic storage, like the Deccan Traps in India, the Western US as well. So that's the kind of big picture. I'm out of time, so I just want to very finally say this is the Carbfix, some of the Carbfix team out in Iceland. I'm just the messenger here. That's some of them. That slide's already out of date because there's about 5 or 6 more now. But I'm happy to answer any questions if we've got enough time now.
Very much, Chris. We have a couple of minutes. I'm seeing 2 hands right in the middle. So we'll start with you on the left. That's okay, and then we'll go.
Hello. Hello. So I'm Roberto from Cardiff University, and that's a great project. I just wanted to ask if there are any studies or any research going on about the fluid flow over time, because I mean, obviously, as you pump the CO2 and it mineralizes, it kind of starts to close the pores that are currently available. So I don't know if there's any research about that, like in the long term.
Yes, well, I guess there's 2 aspects to it. It's one of the big questions that Carbfix always quite rightly gets asked. Essentially, if you're forming minerals, are you not just going to shut down your pore network and just block everything up? So the field evidence for that they've got so far that isn't a problem is because they have not had no loss of injectivity at Carbfix 2. Now, that's only at a kilotons or tens of kiloton scale, right? So as you get to the megaton scale, that's obviously going to be much more of a challenging question to answer. So in terms of how does that work in the field? Well, there's a lot of research going into this idea of clogging versus cracking. Do you induce a stress on the rock as you form your minerals and propagate a fracture network that the fluid's going to exploit? It's an open question, but there's a lot of work going into that. I think the other challenging aspect of it is how do you actually model that dynamic aspect of how your flow network evolves? I don't have the answer to that. It's not my PhD either, unfortunately, but there is a lot of work going into that because that's one of the biggest questions and challenges in terms of the scalability, but it's very much been looked at. I know it doesn't really answer, but
no, thanks.
We've got about 1 minute, so
Okay,
quick.
I'll be as quick as I can. This is kind of a question in 3 parts, so we might have to pick it up later. I'll start by saying I'm a sedimentologist, so I'm the furthest thing from an igneous petrology expert. Can this be applied to sedimentary rocks? You know, is this something that is strictly for basalts? And also, can it be applied to kind of more granitic rocks, which would maybe open it up to kind of onshore UK market? Then the next part of the question is then, can you link that to geothermal activity in terms of if there's a new well being drilled for geothermal, you know, can you get involved in that project? And can that help with the scale up onshore UK?
Okay, I'll try and give like 1-word answers to be really quick. Right. So what we got? We got what was the first one? Sedimentary, sort of. We'll talk about might say that. The granites, sort of, again, and in terms of was it geothermal? Well, yeah, that's what Carbfix 2 is, right? So the idea, I'll be very quick. It's the idea of having 2 revenue streams. So it's kind of like with United Downs, you've got geothermal and you've also got lithium, right?
I went to United Downs a couple of months ago and I asked that question. Yeah, that's kind of the vague response.
Yes. So, but we'll talk more later. I don't want to take it.
Thank you.
That's great. Actually, thank you for the questions and thanks for your prompt response. I actually really enjoy this, like boiling it down into 1-word responses, because quite often we can do that.